Welcome to the online causal inference seminar. Today we are excited to have Emilija Perkovic from the University of Washington, who will speak about causal effects in maximally oriented partially directed acyclic graphs, or MPDAGs, identification and efficient estimation. In Q&A today we have Richard Guo, so please ask many questions. Also, Emma will stop in the middle and take some questions from the audience. After the talk, we will have a discussion by Thomas Richardson, who is also at the University of Washington. And questions here will be handled by Guillaume, so I will now switch over to him. Guillaume.
Thank you, Dominique. So as Dominique said, Richard will be answering your question through the Q&A, so please do not hesitate to ask questions. Emilija will also pause from time to time for questions from the audience. So as usual, we'll select a few questions from the Q&As and ask them live. So if you're selected, I will ask you to raise your hand and I will unmute you. So please don't raise your hand unless I've asked you to do so. All right, thank you very much. And Emilija, whenever you're ready.
All right, thank you. So I need to share my screen again, right?
Yep.
All right, let me do that. Okay. There we go. Actually, can you see my slides? Just checking. Okay, wonderful. All right. So hi, everyone. So I'm Emilija Perkovic. I'm at the University of Washington. I'll be giving a talk today on causal effects in MPDAGs. So I've shortened this from that awful thing you've seen before. Identification and efficient estimation. So I will be presenting essentially work on two papers. The first part is on identification, and then the second part is on the efficient estimation. And so the second part is also joint work with Richard Guo, who is a PhD student at the University of Washington, and he's also kindly agreed to be in the Q&A and answer some questions. So, all right, so let's start. So first, what is kind of this talk about? So we will be trying to estimate total causal effects of some X on Y, so some treatment on some response. And generally the way the gold standard for doing this is by conducting some randomized control studies, right? So, however, here in this talk, I'm going to try and explain how and when, in some cases, you can do it from observational data. So in a randomized control study setting, you have an intervention that sets your treatment to a certain fixed value X. We call this an intervention a do intervention, and we label it with this do of X. And then the total causal effect of X on Y would be some change that happens in the response due to setting this treatment to X. I will talk more about that later, and we want to identify that from observational data. Now, the issue here with doing this from observational data rather from a randomized control studies data is that generally this interventional distribution of the response is different from an observational distribution of the response. Okay. So throughout the talk, I'll be using graphs as kind of tools to represent causal structures. So here on this slide, we have a directed acyclic graph, or a DAG. And each of the nodes in the DAG represents a variable in our causal system. And these arrows represent essentially direct causal relations. Okay. So here we see that we want to identify when we say we want to identify the total causal effect of X on Y, it means we want the effect that propagates through these causal paths in the DAG, right? Through these purple nodes that I labeled. But we also see we have some other paths in the graph that go through these blue nodes that are kind of confounding paths, right? Non-causal paths between X and Y. So what happens when you intervene and set X to a fixed value? Essentially, this is kind of mimicking cutting off these edges in your DAG, right? So once you can manipulate X and set it to some particular value, then these inputs, there's no longer any inputs into X, right? So in this setting, any kind of relationship you can say that between X and Y must be propagated through the causal path, which is why you can kind of identify causal effects in this setting. However, we want to have data from the previous case, right, from this DAG, and we want to kind of mimic what happens here to identify this causal effect. Now, some notation here. So how do we connect these graphs and distributions? So I'll use these terms: observational density for kind of the distribution, the distribution that comes from observational data, and then interventional density or interventional distribution for a distribution under this intervention that sets X to a fixed value. And then we say that a DAG is causal if both these observational densities and all these interventional densities essentially factorize according to the DAG, right? So here you have this joint density of variables, and we see that it factorizes as these marginals of each variable given its parents in the DAG. And then the interventional density factorizes in exactly the same way. So here we switch from something that's interventional to something that's observational, except that you drop just this term that has X in it because X is now fixed, right? So in a particular example, so here we have a little DAG with 3 variables, and the joint distribution here factorizes as, right, Y given its parents in the DAG, so B and X, or its direct causes, right, if you prefer, X given B, and then just B. Once you intervene on X, you essentially drop the blue term here, the one that has X in it. All right, so the other way of saying that is that the observational distribution factorizes according to the DAG, and then all interventional distributions factorize according to some mutilated version of this DAG. Anyway, the point here is that this interventional distribution here that we have is not the same as just kind of the observational distribution when you condition on X. Okay, great. So what is then a total effect? So how do you define that? So a total causal effect, I will use this tau xy to denote it, will be some function of the interventional distribution of the response, right? So some examples of that are these differences in expectation, right? When you set X to X plus 1 or set X to X, it can also be defined as this derivative with respect to X of the expectation of Y. You can use odds ratio, risk ratio, or some other ways of defining the total effect. The common thing is that it's always some function of this interventional distribution of the response, right? So we will then say that a causal effect is identifiable for us from observational data if this distribution can be computed just from the observational joint distribution. Okay, so here we're again making this leap from interventional to observational. And so now, based on the previous slide, you know that, well, if I give you a causal DAG, you can identify any causal effect, right? Because this interventional distribution of Y is just kind of a marginal of the interventional joint distribution. And we know based on the previous slide how to factorize that in terms of these observational factors, then any causal effect given a causal DAG is identifiable, or any total causal effect, let's say that. And so this formula here that I have on this slide is also known as the G formula. And so here I've written it in a bit more of a general way. And it is important for this talk, right? So that's why I'm listing it here. Okay, great. So that seems to solve our problems, right? If we have a DAG, then we know how to do everything, and that's great. The issue, one part of the issue that I'm going to be talking about today is that generally, if you're trying to learn a graph from observational data, then you cannot, in general, learn the true causal DAG from observational data. Now, if you assume that you have no hidden variables, and without making additional assumption, what you can actually learn from data is a structure like this, right? So if you have enough data, you hopefully can learn a structure like this. So this is called a completed partially directed acyclic graph, or a CPDAG. And this is a graph that has both, right, directed and undirected edges. So essentially, this is the summary graph that represents an equivalence class of DAGs. And each of those are equally likely to be your true causal DAG. You just are not sure which one is your true causal DAG, right? So here, this undirected edge, for example, between X and A represents that we are not sure whether in the true causal DAG, the direction is kind of this causal direction from X to A, or this non-causal direction from X to A. Okay. So that's what we can learn from observational data without kind of making additional assumptions, except the no latent variables. But sometimes you might have additional background knowledge, so say from experts or from previous experiments or from some additional assumptions that you're willing to make that can give you some additional orientations. So here I've added now some additional background knowledge in terms of these directed edges in blue to this graph. And now this graph becomes a maximally oriented partially directed acyclic graph for an MPDAG. And I promise this is the last one. And so we see that this one has kind of the same directed edges as the CPDAG plus some extra directed edges. And it still has some undirected edges. Meaning that, right, this is again a summary graph that represents an equivalence class of DAGs. But now this equivalence class is smaller than the one represented by the CPDAG. Okay, so if this is something that you can learn from observational data or observational data and background knowledge, then what kind of causal effects can we identify and estimate in these graphs? So when I say identify, I mean that, right, for each DAG in the equivalence class, the effect would be the same. So you can uniquely identify the effect. Okay, so this is kind of the framework that I have in mind when I think about this project. So we're thinking about kind of going from observational data and perhaps some background knowledge, and we want to get to an estimate of the total causal effect, and we're doing it in 2 steps. So the first step would be to do some kind of causal structure learning to learn this causal graph. And then the second step is the one that I will be focusing on in this talk, right? So in this talk, I'm essentially assuming that I somehow have this causal graph, and then I'm kind of trying to lead you from just a graph to something meaningful in terms of an estimate. Right. Now, this first part, right, how can you actually estimate this causal graph? So I've listed some algorithms here that we have to learn these graphs. They are obviously not perfect, but there is progress being made on this front. But for this talk, right, I will just assume we have some type of graph, and then I will move on to the second part. Now, another important thing to mention here is that here I'm listing DAG, CPDAG, and MPDAG, but the talk is called Identifying Causal Effects in MPDAGs. And this is because you can see DAGs and CPDAGs as special cases of the MPDAG, right? So a DAG, you can see it as kind of an MPDAG where this background knowledge you've included has been fully informative of all the causal directions, whereas in the CPDAG, you can see it as the case where this background knowledge was not informative at all, right? So this kind of class of graphs subsumes the other 2. So just, so you know that when I'm talking about identifying things in MPDAGs, this also, of course, includes DAGs and CPDAGs as well. Okay, great. So of course, we are not working on a vacuum, so there's some existing research on identifying things in these DAGs, CPDAGs, and MPDAGs. And so I'm mentioning some results here. This is by no means a complete list of all possible versions of all of these results, but I'm just mentioning most relevant ones. So one that we've seen already, a graphical criterion for identification is and I realize you cannot see me now. I never thought I'd have the glare problem in Seattle because the sun is too bright, but there we are. Well, sorry, I'm trying to figure it out, but anyway, maybe it's just unavoidable. There we go. I'll just move it. Okay, great. All right, so I'm going to be talking about these 2 different criteria. So the G formula you've already seen on the previous slide before. So this is the necessary and sufficient condition to identify causal effects in DAGs. However, it's kind of unclear how you can apply it to these CPDAGs and MPDAGs. Then there is another popular graphical criteria for identification, which is adjustment criterion. So here I've listed the generalized adjustment. And this one is sufficient for identification, but it is not necessary. And again, I'm not mentioning all the work here that's been done on adjustments. So starting from Pearl's backdoor criterion through Ilya's adjustment criterion to many other iterations, the generalized backdoor and so on. So I'm just mentioning part of the work here. But this is the criterion that is so this version that I'm mentioning is applicable in all 3 of these graph classes. And as far as adjustment goes, it is the most complete one. This is why that one is chosen. So other names for adjustment is kind of adjusting for confounders or backdoor adjustment. Okay, so just to give you an idea, again, this is the G formula here that we had from the DAG. And the adjustment criterion says that essentially, if you have that some set is an adjustment set of variables, if this interventional distribution can be factorized in this way, right? It's quite a nice and kind of elegant formula. However, it is not complete for identification. So the question is kind of, can we generalize this G formula, or can we get something that is necessary and sufficient in these other graph classes as well? And since I'm talking to you, I'm guessing that the answer is yes, right? So the first result that I'm going to be talking about is this causal identification formula, which is essentially a generalization of the G formula for these MPDAGs and MPDAGs. And as such, it also inherits this nice property that it's necessary and sufficient for identification. Now, you can already see that this generalized adjustment, for example, is sufficient but not complete in DAGs. So let me give a little disclaimer here, is that in the case where you have only single treatment and single response, it turns out that generalized adjustment is kind of almost complete. So whenever the effect is identifiable, it will give you an estimator. But so this one directional arrow refers more kind of to the setting where you have essentially more than one treatment or more than one response. I'll talk a bit more about that later. So what does this causal identification formula look like? It looks like this. It's a bit scary, but we'll get through it. So it has a few parts. So the first part here in purple is a necessary and sufficient condition for identification of these causal effects. And it says that all possibly causal paths from your treatment to your response must start with a directed edge. So this is a necessary and sufficient condition for identification. And why is it important? So if you have a path like this, so X, undirected arrow A, and then directed arrow Y, then we say that this effect is not identifiable. And so why is that? Because we don't essentially know whether this path will be a confounding path or a causal path in your true causal DAG, right? So you kind of don't know whether you should account for this effect through A as kind of part of your causal effect, or if you should in some ways adjust for this confounder, right? So once you have this purple condition satisfied, then you can identify your total effect through this formula. And this formula looks very much kind of like the G formula we had on the previous slide. So it again consists of kind of a product of some marginals or some sets given their parents. So now the difference is that these are sets, they're no longer necessarily variables in this graph. And then you also integrate over something that does not contain Y. So how do you kind of come up with this? So the first thing you need to do is you need this set of ancestors of Y in this particular graph minus Y. So you need all of the nodes in G that have a causal path to Y, not through X. So those are all the variables or nodes that will figure essentially in this formula. So you need ancestors of Y that are ancestors of Y not through X. And then these factors are in terms of this decomposition here, where each element in this decomposition is a maximal connected component in the undirected subgraph, in the induced undirected subgraph of G, right? Maximal connected component of this set in particular. And so, and then once you have that, you can decompose your f of Y to X in this particular way. Okay. So one nice thing about this is that if you just think that G here is a DAG, then actually this formula simply kind of implies the formulas we had in the beginning, right? The ones that define a causal DAG. So this kind of general factorization and this truncated factorization formula. So in that sense, it's a generalization of those results and the and the G formula. Okay, so how do we actually use this? So let's go back to our DAG from the beginning. And I've said that, so in this case, it's not a particularly interesting case because here we know that the causal effect is identifiable in all ways through G formula, through adjustment, and through our causal identification formula. But what if we change this E to be an X2? So now suppose we are interested in the causal effect of X1 and X2 on Y, right? So this can be if you have, let's say, some sequential treatment or something like that. And so for this particular graph, there is no adjustment set that you can use. So it's still a DAG, so you can still use the G formula, but the adjustment set cannot be used in this case. And why is that? So for people just slightly who are familiar with adjustment, this is due to kind of this node here, right? So when you are using covariate adjustment, what you're trying to do is you're trying to adjust for confounders, and you also don't want to block causal paths. But here the issue is that A is a confounder for X2 and Y, right? But A is also on the causal path from X1 to Y. So in some sense, you both want to adjust for A for X in terms of X2, and you also don't want to adjust for A in terms of X1. So here there is no adjustment set. But there is a G formula. So just to make it interesting, let's look at the MPDAG version of this, right? And so how do we come up with this causal identification formula here? So first thing is to check that all possibly causal paths start with a directed edge out of X. And this is of course satisfied here. Sorry, since all the edges next to X1 and X2 are directed. Then the second part would be to find all of these ancestors of Y that are ancestors of Y not through X. So to do that, easiest way is to just remove your X and then look at what are ancestors of Y. So here everything is an ancestor of Y. Next, in order to get each factor in the causal identification formula, you want to partition this set S and Y into the maximally undirected components, right? So here, by looking at the undirected subgraph, we can see that the components here, or we also call them buckets, are this BCD, A, and then Y. And I've also ordered them here in this topological, in their topological ordering according to this MPDAG, right? So the B, C, and D precedes A, and then A also precedes Y. Okay, and so once you have that, you can kind of write your causal identification formula as so. So it would just be, so you integrate over these ABCDs, and then you have f of y given its parents in this MPDAG, so A, X2, C, B, C, and D, A given its parents, and B, C, D. So B, C, D you further do not decompose because they are altogether make up an undirected component here, right? So we do not know in the true causal DAG what is the causal ordering within this component, right? So we just choose to keep this component altogether. And so how do we get this? So I thought I'd do a little proof sketch. I think I have time. So it's a very kind of intuitive idea, is that you first just kind of include with, include the set S. You integrate over everything. Then you use just the chain rule in kind of the reverse of this topological ordering. So you have Y given everything else, then A given everything else, and then B, C, D. And then once you have that, you can remove everything that is not a parent. So Y, these are all parents. A, C is not a parent, so you can remove it. And then in the last step, the only thing that's done is that you can remove now finally this do, so you can make this change from an interventional to an observational distribution and just leave in the x's that are actually parents of Y, right? So what we have here now is this formula in terms of Y given its parents, A given its parents, and then just BCD is left, right? So this is kind of how our causal effect also propagates through this graph. It propagates through these edges and then also through this one. Okay, great. And naturally, it's a generalization of the G formula in that case as well. All right. So we have that part now. So the question is, what can we do with it, right? So can we use this to kind of efficiently estimate the causal effect? And so this is part of the work with Richard that is available now on arXiv. So for this part of the talk, I will additionally assume linearity. So I will assume that the data is generated by a linear structural equation model. Okay. And also I will do a bit of a switch on you here with the notation. Apologize, this is just to keep it consistent with kind of the general SEM literature, right? So here now you see there is no X in this graph anymore. Also the graph has changed. That's because I'm using X now to denote my entire random vector, and I'm using the node names here to just as a subscript of this random vector, right? To index each of the variables. So here, this is the DAG that I will use as an example throughout this part of the talk. And so when I say that it's generated by a linear SEM, I mean that each variable here is a linear combination of its parents in the DAG. So xy is equal to some combination of xe and xc plus some error term eu, right? Where this, or error term ey in the case of y, right? Where the expectation, I think I'm using the cursor too much, so just trying to be conscious of that. Right, where these errors have mean 0, a constant variance, and also in the case when you know the causal DAG, these errors are mutually independent, right? Because we don't have any latent variables, there will be assumed to be mutually independent, right? So for example, in terms of this notation, y will, or xy will be equal to gamma ey plus gamma cy plus epsilon ey, sorry. Okay. And so these gamma terms are known as edge weights or direct effects in this particular case. And so suppose that now we're interested in the total effect of A on Y. So A now becomes our treatment. And for simplicity, for the rest of the talk, I will choose to have only one treatment. This method will also work for you if you have more than one treatment, just for kind of the simplicity. I'm not getting into that here. Okay. So how can you identify what is a total causal effect in this setting? So generally, a natural way to define it is as this derivative of the expectation of the response when you intervene and set x to a with respect to the treatment, right? And so then, of course, you can estimate this with the G formula here because we're in the DAG. So if you replace the G formula and then do some computation, what you end up with is this kind of sum product of these edge weights or edge coefficients along these causal paths, right? You can also obtain the same thing by the path tracing rules of Wright. So both by G formula and path tracing rules of Wright, you have that this total effect can be written in this way. So what this suggests to us, right, is that if we want to estimate the total effect, maybe one way to do it is to kind of estimate each of these gammas and then do a plug-in estimator, right? So you can estimate each of these individual gamma edge weights by regressing. So in the linear Gaussian case, regressing definitely y on E and C. Right, regressing each node on its parents will give you kind of the MLE here for the plugin of these gammas. Additionally, in this case, we also have an adjustment set that can be used to estimate the causal effect. So the total causal effect can also be identified through this formula, right? So E is the only confounder between A and Y. So you can simply adjust for E in order for you to obtain this causal effect, right? And so what this essentially recommends to us in the Gaussian setting, at least, is to estimate this total effect as the least squares coefficient in this adjusted regression, where you regress y on A and E, right? So this is where the adjustment essentially gets its name from this adjusted regression. So we now have two different estimators we could use to estimate this total causal effect. In general, you may have more than one adjustment set that you can use. So the question is, which estimator would be more efficient, and what do you do if you do not know the causal DAG? So let's talk about existing work again. So one thing is that assuming Gaussian errors and given a particular DAG, Hayashi and Kuroki showed that the path tracing plugin estimator, or this G formula estimator, is more efficient than covariate adjustment, right? It also essentially forms like a plugin MLE. So the path tracing based estimator forms the plugin MLE. But the question is, what if you do not have a DAG? So there is some recent work on adjustment in terms of what adjustment set would be the best one to use if you have many of them to use to kind of identify your causal effect. So Henkel et al. And Witte et al. Characterize an optimal covariate adjustment sets in DAGs, CPDAGs, and MPDAGs, right? So we know how to choose an optimal adjustment set. But now the question is, since kind of the G formula would be more efficient in the DAG, would our version, our generalization of the causal identification formula be more efficient in these other graphs? And again, the answer will be yes, since I'm talking about this. Okay, Oh, I think I was meant to stop at some point to ask for questions. So let me do that now, actually, because otherwise I just go into this mode. So if there's any questions, I'm happy to make a break.
Thanks, Emma. Yeah, so I think Dominic has a question. Do you wanna ask it, Dominic?
So about the first part, I just wanted
Sure.
to ask about the algorithm. So can you compute them relatively quickly? So how does it scale roughly?
Oh, it's so it's a good question. So it's not there is no okay. One thing that the way that I've presented this is that you first choose this set and then you partition it. But what you can do actually is you can do it the other way around. So what I mean by that is you can first take your undirected subgraph and partition it into these kind of buckets, right? These undirected components, and then you can intersect each one of these with this set to obtain this, right? So you essentially, in order to get this decomposition, you only need to do this kind of bucket decomposition, this maximal connected component decomposition once, and you need to compute this set. So that's the only kind of computational requirements in order to output something like this. So it's not really that intense, essentially. It's kind of a few depth first searches should be, I think, okay.
Okay, just one very quick last question. So you, in the beginning, the first half, you used, that was a completely non-parametric setting.
Yes.
Do the adjustment sets change if you make also a linearity assumption there?
The adjustment sets, you mean?
Do you get more adjustment sets?
No, actually. So that's a great question too. So that's true. So this formula or this results on, sorry that I'm going through the slides so much. Where is it? This one, right? So this is a kind of a non-parametric or semi-parametric, whatever you want to call it, result. But the proof essentially uses linear sems. So it's kind of also a complete result in terms of linearity. So you don't get anything more.
Great, thanks.
No problem. All right, is that all? Okay, so I will make you suffer through me going through the slides one more time. And I think we were here, right? So the question is, how do we do this in an MPDAG or a CPDAG? All right, so again, let's go back to our example of the DAG and let's see what is the issue with having a CPDAG or an MPDAG, right? So we have this kind of form for our linear sem. We can, of course, rewrite it in this matrix form as well, where we have this now gamma matrix and this gamma ij, where if I is not a parent of j, then this gamma ij is 0. So if A is not a parent of B, this would be 0, meaning for gamma BA is 0 and gamma AB not necessarily 0, right? So the problem is once you, let's go through the MPDAG. So this is an MPDAG, a representation of the DAG, right? So this is a summary graph that definitely includes the DAG we had on the previous slide, but it also includes some other DAGs. So we have these two undirected edges and the rest are directed. Now the issue is once you have a graph like this, now this gamma matrix is no longer identifiable, right? And this is the way that we were suggesting that you compute the G formulas by kind of essentially computing your gamma matrix and then doing a plug-in estimator where you plug in these individual edge weights to compute your total effect. But now it's no longer identifiable. So what can we do here? So the idea here is just to remember the causal identification formula and then think in terms of these buckets or these maximal undirected connected components, right? So let's look at what are the connected components here. So we have E, A, B, C, D, and Y. Again, I've ordered them according to their directed part, right? So E precedes A because E is a cause of A and so on. And what you can notice is now that we've split them into these undirected parts, this between bucket or like between these different sets, the effect is identifiable, right? We don't have any more undirected edges between these buckets. So anything in between, in some sense, is identifiable. And there is another important thing that happens here, which we use to show efficiency, which is called the restrictive property. And that's essentially that each node in a bucket has the same set of out-of-bucket or external parents, right? So here, if you look at this BCD component or bucket, you see that A is a parent of B, but it's also a parent of C and D. So in other words, it's not allowed that A, for example, is only a parent of B. It must also be a parent of everything else in the bucket. Okay, and we can then use this fact to essentially reparametrize our original SEM. So now we know that for each node in the bucket, right, in any of these buckets, it's essentially in the causal DAG, it would be a linear combination of its external out-of-bucket parents, so in this case A, and then perhaps also some within bucket parents, right? So we can treat this, rewrite the SEM in kind of a blockwise fashion according to these buckets. Right, so this is kind of the main thing in this block recursive reparametrization, right? So each bucket is essentially a linear combination of its out of bucket parents. So I'm just using this parent BI to denote everything out of bucket. So this doesn't include anything in BI, plus perhaps some within bucket things. And of course that can be rewritten in this way. So now we have lambda instead of gamma, and we have epsilon instead of this E here. Okay. So essentially this is now also a block instead of a single variable in the previous case. So we have this one block as a essentially linear combination of its parents, out of block parents, plus some error term. And you can imagine that since we can do this for each bucket, we can essentially in the end stack these different blocks to make up the big matrix lambda, which is going to be the first result, right? So if you have this bucket decomposition of all of your variables in the MPDAG, then you can rewrite that original SEM that had a gamma here, gamma matrix and errors E here, with this lambda matrix, which is now block diagonal and upper triangular. I'm always confused by the transpose. And also so that, right, for each element of this lambda matrix, if J belongs to a bucket BK and I is not an external parent, we will force this entry to be 0, right? So the only non-zero possible entries here are the ones between the buckets. Also, another thing that you can notice based on kind of the rewriting is obviously the entries of this lambda matrix are not the same as the entries of the gamma matrix originally. Another important thing that happens here is that it turns out that these between bucket errors, right, these error vectors are mutually independent. So they are not independent within the bucket necessarily, but between the bucket, they are independent. And so two nice things happen as a result of this reparametrization. So one thing is that we can identify this total effect just using the lambda matrix, right? So this error distribution is kind of not important for us. So we can identify it in this particular way, where S is again the set same from the causal identification formula. So these are ancestors of Y, not through A in this case, right? And so here this A and S subscript denotes A row and then all S columns, right? All columns that are indexed by these nodes. Okay, and then another thing that happens as a result of the restrictive property is that for Gaussian errors, the maximum likelihood estimator for each of these blocks that make up this big lambda matrix is just the least squares coefficient, so least squares estimator of this BI bucket on its external parents, right? And so that leads us to the estimator we are proposing here, which we call G regression. So technically, so actually what I'm saying here is that we have now reparametrized the SEM in this form, and we now can estimate all elements of this new lambda matrix. So why don't we do that in this way through least squares, and then form our G regression estimator essentially as a plugin of this. So it's essentially a plugin estimator based on this reparametrization of the SEM. And so this is kind of the main result, and Richard is definitely the main driving force behind having this result. So as you can see, this estimator that we're proposing is just a plugin of what we had on the previous slide. So we just give hats here and replace everything with this least square coefficient. And then we can show that for any consistent estimator of the total effect that is a differentiable function of the sample covariance, the G regression estimator, so this one here, will have a asymptotic variance that's smaller or equal to the asymptotic variance of this other estimator. Right. So this means that within kind of consistent estimators that are based on kind of the first two moments, this would be the best thing to do. So you might wonder what estimators are included in this case. So that includes the covariate adjustment-based estimators, and also these two ones that I will talk more about later, estimators based on recursive regressions and modified Cholesky decomposition from the joint IDA paper, if people are familiar with that. I'll talk more about this again in a few slides. Okay, great. So what is actually our G regression suggesting that we do for this particular MPDAG? So here, the total effect, right? We can replace our causal identification formula to see what we would get. And so what this essentially now suggests that we should do, and what we do by G regression, is you suggest a plug-in estimator where you first regress Y on its parents, then you regress C on its parents, and you combine essentially this coefficient next to C and this coefficient next to A. So the product of these two will give you the total effect in this case. Right? This is what essentially is suggested that we do. Okay, great. Okay, I'm good on time. Awesome. So let's look at some simulations, right? I'm claiming that we do better than these other estimators. Now, another thing that I will point out is that we don't give you kind of a very nice formula for this asymptotic variance like some other work like on covariate adjustment does, but this guarantees that the variance should be smaller in this case. So how do we do a simulation? So first we draw a DAG from a random graph ensemble. I think we use Erdos-Renyi in the paper. And also we choose a certain number of nodes, a certain number of expected neighborhood size. Then we take the CPDAG of this DAG, simulate data from a linear SEM, given the DAG, right, with various error types. And we choose then A and Y such that this tau AY, the total effect of AY, is identified in the CPDAG. So the CPDAG will now serve as our MPDAG here. And then we compute the squared error of kind of the true effect minus the estimated effect for each of the following estimators, right? So we of course computed for G regression, but then we also computed for this optimal adjustment set of Henkel et al. And we also computed for these two IDA-based estimators. So I will say it's not a very fair comparison because this is not what these estimators were designed to do. So the purpose of these two estimators is they only need the parent set of your treatment to give you a consistent estimate of your effect, right? So they need kind of strictly less information than what we have. And then essentially they use these parent set to in some ways adjust for confounders. And there's two ways of doing that. One is through using these modified Cholesky decompositions, and the other one is based on some recursive regressions. Okay, so let's look how we fare in the DAG setting. And it's a lot, but let's get through it. So these are just some violin plots displaying relative squared errors. So on top is the error of one of the other competing estimators, and on the bottom we have our G regression error. So if this ratio is bigger than 1, right, then we are doing better essentially. And so here I'm assuming we have given the true DAG, and you have different settings depending on the number of nodes or variables and the sample size of the data that is generated. And so you have these violin plots. So what you can see based on them is when we have only a single treatment, we don't do that much better than adjustment, right? When you have the more treatments you have, the better we do. But as you can see, compared to adjustment, since this mode is still at 1, we don't do that much better compared to the optimal adjustment set. We still do better, but it's not by perhaps a giant amount. Compared to the other two estimators, we do much better. And that is to be expected, especially comparing to the result on optimal adjustment set, where was noticed that essentially the parent set is not a good thing to adjust for, right? It's somehow inefficient, right? And since these two use parent sets, it's not surprising that this method does much better. All right. So this is in the DAG case. So another important thing here to note is that, remember I said that we simulate results such that the effect is identifiable in the CPDAG, but here I'm giving the results of when is this effect identifiable given these other estimators, right? So again, it's perhaps not very fair towards these two because this is not what they were designed to do, but compared to adjustment, right? You can see in the case where you have only a single treatment, it's the same. So all of the effects that are identified by adjustment will also be identified by the G-regression and vice versa. But then as you increase the number of treatments, there's more and more effects that cannot be identified with the adjustment estimator. Okay, so this is all of the effects that you would miss and not be able to estimate with these other estimators. And so what happens when we try to estimate the CPDAG with GES and then do essentially the same thing where we compare these relative errors is, well, this slide happens, right? So there is still a bit of a gain, but it's definitely not as pronounced as in the DAG case. That's the main takeaway, right? So the adjustment set still does fairly well. I forgot to say that this plus denotes, I think, the median, and then the dot is the geometric median. But yes, so generally we still do better, but the improvement is not as drastic as in the previous case. Okay, so that was it. So I presented the work from these two projects on these two parts. We have an R package that's on GitHub that you can play around with. Something that I didn't get a chance to mention is that there is work on adjustment and on efficiency beyond the linear SEM setting. That's by Rudnitsky and Smokler, and that is perhaps also worth considering applying to our own estimator, but we have not done anything like that. All right, thank you.
All right, great. Thanks, Emma, for the great talk. We'll now switch over to the discussion. So we have Thomas Richardson send some slides, and then after that, Emma can respond if she wants. Thomas?
Great. Can you hear me? You see the slides?
Yes.
Okay, great. All good? So thank you for asking me to discuss this paper. It's a very interesting paper. So I will just start by, I don't have a lot to say, but I will comment on some related work. Just briefly talk about this restrictive property and G-regression, and then a little bit about MPDAGs versus CPDAGs, and linearity and some possible extensions. So connection to previous work. So in the beginning, there was IDA, which was a method that could be used after you had run a graph learning algorithm to estimate a distribution arising from a single point intervention, and that had 3 steps. So the first step was obviously try to work out the graph, try to recover the graph from data via estimating a CPDAG by one of the standard methods, and then extract. That won't necessarily tell you the parent sets of the intervention nodes, so you then extract all the possible parent sets of the intervention node you're interested in, and then use adjustment to estimate the effect of A on Y, which may give you, in general, could give you many estimates of the effect. So then the next iteration was to think about, could we extend this to having multiple intervention nodes? And so in order to do that, there were two things we had to do. We still estimated the CPDAG. We then wanted to extract jointly valid parent sets for the intervention nodes. So again, remember, this is a context where the CPDAG will not give you the full structure of the graph. It'll just give you it'll allow you to work out that your graph is in a big collection of graphs that have certain features in common. So then we want to extract the jointly valid parent sets, and then having done that, estimate the effect of the interventions on the outcome. And the way that we did this was using knowledge solely of the sets of parents in the intervention nodes. And that was, again, a little bit the spirit of the original IDA algorithm. And we came up with two different methods that I won't go into details of here. One was based on recursive regressions, and the other used a modified Cholesky decomposition, which was a little bit connected to ideas of fixing, and that Ilya Spitzer talked about a few in a prior presentation. So we had these two methods, and they were clearly different. They gave slightly different answers, and in simulations, neither dominated, which of course could lead you to the conclusion that neither is that both are inefficient. And in a certain sense, this work resolves this open question, so it provides an efficient method, G-regression, which thus supersedes the previous approaches. So I think it's a great improvement, and it's added a lot of clarity, and it's a huge leap forwards. The new, as Emma mentioned briefly, the new method does require a CPDAG or MPDAG, whereas this last step, just the step 3 star, the other methods that we came up with only require you to know the parent sets, but it's not really clear to me that there are many situations where the parent sets are known without knowing more structure. And certainly in the paper we presented these, our initial step was to learn a CPDAG. So. Okay, a quick comment on this restrictive property. So I saw actually in the chat there were some questions about this, and I thought maybe the word restrictive here, typically when, at least the statisticians, when we see restrictive, we sort of think that's going to mean that we're making some assumption here, and it isn't an assumption. It's a structural property that essentially, if you learn a CPDAG, so that means if there's some true underlying DAG, and then you then consider the class of all other DAGs on the same variables that represent the same model, so that have the same deseparation relations, then you end up with this object, the CPDAG, where so all those DAGs will have the same adjacencies, but they may have different, the edges may be oriented in different directions. And if we keep a directed edge when the edge is the same in all of them, and an undirected edge when it differs, we'll end up with this structure. And it will be the case that undirected connected components in that graph have certain properties. They will be caudal, but in addition, they will all share the same parents. So if another vertex is a parent of one vertex in that undirected component, then it will be a parent of all of them. And you could also add in additional knowledge. So the distinction between CPDAG and MPDAG is that there's extra knowledge that's being added in the MPDAG. And there are then orientation rules that allow you to work out the logical consequences of those, and the resulting object will still have this property, provided that we define the undirected chain components in the way that Emma and Richard did. Okay, so G-regression, the key property of the method that's being introduced in this paper is that it does not require estimation of parameters associated with edges within buckets. So the buckets are just sets of variables that are connected by undirected paths. And the key property of this procedure is that it can estimate the causal effect without needing to estimate the parameters relating to these undirected components. And so it's sort of some simple corollaries of that are that, for example, if this was your graph, So here we've got buckets A, B, and C, Y. Then the MLE that you'll obtain for the effect of A on Y would be the same as it would be if there was actually no edge between B and C. So if we fitted this graph and then looked at the MLE, we would get the same estimate. Or alternatively, you know, we could, if we were thinking of things like path diagram models with correlated areas, we could allow the areas to be correlated within buckets. So all of those would all give the same estimate of the causal effect of A on Y. So another innovation of this work is that we don't just have a CPDAG. We're not just recovering a graph from data. We're also allowing background knowledge that to be incorporated. So essentially allowing some undirected edges like this in the CPDAG could be replaced. And so natural question is, what's the role of these extra directed edges? And would a subset suffice for identification? So for example, supposing two different people disagree about which extra edges they think which edges could be oriented, would a subset sometimes suffice? And would that affect the G-regression estimator? And might it affect the expression of the G-regression estimator? So the extra edges clearly do matter. So here's a trivial example. This is a CPDAG where we've just got two variables. If subsequently our background knowledge tells us that X causes Y, then now we can identify the effect of X on Y. But in general, for identification, I think it would suffice to keep solely those additional edges that are directed out of intervention nodes on proper causal paths. So in general, you could do with fewer extra edges. You only need those. I don't think you need any more directed edges than those that come out of intervention nodes, additional ones. And I think that if you did that, so if you use fewer of these extra directed edges, the resulting G regression estimator would actually be identical to that you would get from the MPDAG with the full set of extra directed edges. And then a minor point is that it might give you, if you have fewer extra directed edges, you might get a slightly simpler form for the estimator. So here, to just see a little example of this. So these two graphs over here on the left, we've got this is an MPDAG. This is also an MPDAG, but it's an MPDAG with fewer extra edges. So here we've allowed this edge to be undirected. So as I said earlier, all of these models will give the same estimate, same G regression estimate for the effect of A on Y. But in this model, we would be regressing C on B and A, whereas in this model, we would just regress C on A here, and we would just regress B on A here. So although we'll end up with the same statistic for our estimate of the effect of A on Y, because of Cochrane's identity, basically saying that the regression of C on A can be decomposed in this way into these regression coefficients, regressing C on A and B, and C on B and A, and B on A. But so you get a slightly simpler form, and indeed, you could also use less data. So in the sense that to estimate this, you would need to have joint data on A, B, and C, whereas if for some reason you're in a setting where you only had data on A and B, and A and C, and B, C, and Y, maybe for privacy reasons or something, you could still estimate it, whereas this form, you would require joint data on A, B, and C. Okay, and then, yeah, so one other comment here is that I do think that so Emma's talk, there was the first part that was non-parametric, and then the second part on G regression was linear. And I think the sort of the magic that's making it possible to rewrite the estimator, so getting the same estimator from all of these models, I think that is relying quite heavily on linearity, because you will need, if this is the true structure and we're not in a linear setting, I think you will need the joint distribution over A, B, and C in general. And then extensions, there are obviously lots of extensions here. Sort of assuming that there's a DAG with no hidden variables is maybe appropriate in some settings, but that seems to be quite a strong assumption. And I spent a certain amount of time trying to relax it in other settings. And then, there are models with bidirected edges that capture some of, allow for some hidden variables, or cyclic models are also extensions, but that's it. But an excellent paper, and thank you very much for inviting me to discuss it. And also thanks to the organizers for an excellent sequence of causal inference seminars.
Great, thanks, Thomas. Emma, do you want to respond?
Yeah, sure. So yes, happy to respond, and also join Thomas in saying a big thank you to everyone. So yes, actually, so we're actually, Richard and I are kind of, we're thinking along the same lines, right? So it seems that some of the background knowledge is not needed, right, to identify the set. And just looking at the causal identification formula, what you can see is that as long as you can orient these things on proper, possibly causal paths, you can get identification, right? So we actually do have kind of a project that's related to that, kind of looking at what would be kind of the minimum background knowledge that you would need to add to identify different causal effects. Our motivation was slightly different. So what Thomas said in terms of, because of the kind of Cochrane's formula, you would have the same effect in theory always. So, right, so these different effects that you would get with adding more background knowledge should not be different. But perhaps, right, because we are not in a theoretical setting, in a practical setting, they might be slightly different because we're doing some numerical computations, right? So our motivation was kind of so yes, we are working on a project to kind of consider that as well. And yes, the other comment about linearity being very important, yes, that's definitely the case. So if you have some interactions of some kind, that would not be applicable anymore. Or the same procedure. Yeah. Yeah,
right.
that's it.
All right, great. Thanks, Emma. So I think it's now slowly time to wrap up. So first, thank you very much, Emma, for a great talk. Thanks, Thomas, for an interesting discussion, and thanks, Richard, for helping us out in Q&A. Yeah, and thank you all for joining. I hope you have a nice week, and hope to see you all next time. Hope you stay safe.
Thank you.